Thank you. I've been asked to say a little bit about this from the point of view of science. So today you're going to be hearing a lot about the engineering and a lot about cool robots. But the path forward, well, we're NASA, we're JPL. We want to go somewhat beyond mines and caves on Earth. So over the past few decades, really, of planetary exploration, we've learned a lot about the surfaces of other worlds. And there is a huge drive on to explore the surface of Mars in order to look for signs of life, for signs of water. However, over the last decade, I think there's been a growing awareness that the story of life on Mars is complex. It's certainly not easy to address. And like with many other bodies, the next step may well involve going underground. And this is where planetary caves come in. Over the past decade or so, there was the initial discovery over a decade ago of pits in the surfaces of other worlds that has led to the realization there may well be vast cave systems under the surfaces of both Moon and Mars, and there are even hints of them out in Titan. The caves we see on these two local neighbors are associated with volcanism. And so these are not like the Carlsbad Caverns karst cave systems you see on Earth, but instead they are more like what you see in Hawaii, in New Mexico, where you get these vast basaltic lava flow systems, tubes forming under the surface and skylights into them. We've seen hundreds of these, possibly even hints of thousands of them on Mars, and they're becoming more and more intriguing to the planetary community every day. So they're very hard to make out that there's truly a cave here, but what you can probably see is that it's an unusual shaped crater that if you look at them from multiple angles, you can actually tell that they go deeper into the subsurface. So their subsurface volumes are far greater than that collapse. Why they're really, really interesting is that on Earth, at least, caves form their own ecosystem niches. So by that, we mean that the environment is somewhat isolated from the outside world. And in addition, the environmental conditions are unique. There's lots of unusual chemistry going on there, new minerals, preservation of volatile records, and indeed, they seem to have their own life systems. And so in a world like Mars that is potentially hostile on the surface to life, you've got perchlorates, you've got space weather, you've got radiation. Somewhere in the subsurface, like a cave, could be an extremely appealing target, largely due to the stability. Another reason to go to caves is human exploration. We're hearing a lot about this from NASA at the moment. But these subsurface voids, well, humans have been staying in caves for long parts of human history. People still live in caves. But certainly at different parts of time, caves were the most amazing protective environments. The problem is studying them from space is hard. This is an early interpretation of a potential cave entrance on Mars, and basically it's a little black dot on the surface. You've seen the holes that we see already. This is unusual, and this may well have been formed by a subglacial cave where the glacier vanished afterwards. But it's difficult to actually learn much about the caves from the surface. We've got some radar sounding and gravity data that perhaps hints that there may be more extended caves, but it's right at the edge of signal to noise, and not everyone is convinced by it. So, you saw this right at the start. Back in 2014, there was a JPL study looking into what we would need to go into a cave, given that we haven't actually done much reconnaissance of it. And so we identified 6 areas of technical fidelity against which we needed fairly substantial advances before we could even potentially go into those caves. Now, you may have heard of the Moondiver mission that's being led by Rollercopter at JPL. They've made some pretty big advances against some of these, not all of them. They don't go deep into a cave, they just explore the skylight. But what I'm going to be talking today, well, what they're going to be talking today about is the possibility of Nebula being the component that contributes to control and autonomy, so the ability to make the navigation decisions. But I'm particularly excited about this, not just because it addresses one of these areas, but because it can have major impact on most of these. In terms of access and mobility, it simplifies the problem to actually be able to explore in situ what is going on. But also, autonomy allows reduced communication requirements, reduced power requirements, and also it acts as an instrument on its own. It can do 3D mapping, which is the first kind of instrument you want when you're exploring an area, images and 3D maps. And so Nebula, which you'll be hearing a lot about, has outstanding potential to be an enabler for these future missions, which is why I'm so excited to introduce the speakers coming on. But in summary, subsurface exploration is where NASA seems to be moving around to. The Decadal Survey is almost certainly going to be talking far more about these subsurface environments than ever before. So thank you very much, and I'd like to hand over to the next speaker.
Okay, hello everyone. My name is Aliaga. I'm representing Team CoSTAR today here, and I'm very excited to tell you about this incredible project and what we have been working on for the last 2 years. So my talk is going to be structured in 2 parts. First, I will go over the competition and what we have been working on, and then I will talk about Nebula, which is kind of the brain behind these robots. And it's a capability we are developing far beyond the Sub-T challenge, and we're trying to add it to the JPL capability library for potential future missions. So what is Subterranean Challenge? The goal here, the mission is autonomously explore GPS denied, communication denied, underground environments like caves and tunnels. We have to cover up to 8-kilometer long cave networks only in less than 60 minutes. And that's what makes this a DARPA challenge. It's a goal far beyond the current state of the art or state of the practice. And what adds to its difficulty is there is no prior map, no information a priori about the environment, and no human is allowed to enter the course during the competition or before the competition at any time. We did a little bit of search, see, okay, what is out there, and this is the Hollywood version. So I'll start with this. So this is from movie Prometheus, and this is exactly what the sponsor DARPA wants us to do. So the guy is, letting the robots go. It's a multi-robot. It does mapping of lava tubes, and it's actually a planetary exploration mission. And this is the operation console that the human supervisor looks at the data coming back, and that's again what the sponsor wants us to do, But then we realize this is year 2200, so I think much earlier than that, hopefully we'll get to those kind of capabilities. So for a sponsor to motivate that kind of autonomy, they distribute 20 objects in this environment at different locations, objects like CO2 concentration rooms, water, artifacts, and so on. And each team can get 1 point per object if we can detect the object, if we can localize it, find its location with only at most 5-meter error in 8-kilometer long course. And then also we have to, send the information back to surface within that hour. Either by robots coming back or somehow communicating it. Like other DARPA challenges, the schedule is quite aggressive. It's a 3-year project. We just finished the first year. Each year there's a major competition, first in a tunnel man-made environment, then in a natural environment, caves, and finally in final event, August of 2021, it will be a mix of man-made and natural environments. And each year there's also a minor event or a qualification event in March-February timeframe, and we are only about a month away from the next event. So what happened in 2019 was there were more than 50 institutions in the tunnel competition, first round of the competition, in the form of 11 teams. 6 of them were DARPA funded, including our team. And there were a huge variety of technologies and robots, and here you just see very small subset of teams and some of the robots that participate in the competition. The balloon one actually won the fan favorite robot of the competition. It was a very cool robot. So what about JPL team? So we also went to the competition with a multi-robot solution. Hence the name, Collaborative Subterranean Autonomous Robots, or CoSTAR, our team's name. And it was a collaboration between JPL, MIT, Caltech, and KAIST. In terms of concept of operation, we relied on a multi-robot solution with complementary capabilities. And robots were being dispatched and distributed to the different parts of the course. As they enter, we try to drop these communication nodes like breadcrumbs and maintain communication to the robots to the extent possible. But very soon you lose that communication, and robots are on their own and doing full autonomous mission and trying to communicate data back by coming back or sending a data mule to bring the data back. And here you see some of the robots we used in the first year, and some of them we deployed, and you see them also on the stage. And I'm excited actually to share with you the latest addition to our robotic family. Spot. So our autonomy, grabbed attention of Boston Dynamics, so they send us these robots that we are going to use in the next round of competition. We are very excited about it. And at the top, you see the payload. This is Nebula, our autonomy framework that we are going to talk more about, that gives intelligence to these robots and enable them to go from here, let's say, to the west gate of JPL. So now I have this short video that gives you a little bit of impression of the course and some of how we did in the 2019 event and some of our capabilities. So what you see here is called the staging area. Our team members are there and preparing the robots and sending them into the course. As I mentioned, no human is involved. There's just one sole operator. It's Kian. Where are you in the audience? Yeah, Kian is there. So he's the only person that can see data coming from robots, if any, because communication is difficult. But if something comes, he's the only one that is who is allowed to see the data. So you don't see him here in this picture, but he's in the background. And the rest of the team is just preparing hardware and letting them, when the competition starts, they let the robots go autonomously. So the robots enter the course. This is our entry into the tunnel competition in 2019. This is what Kian, our sole human supervisor, sees. He sees the map being created while we have communication to the robots. And in the right, he sees different robots and how the mission is progressing. Robots are entering into the course. And they start exploring. They start autonomously go search this environment for artifacts and going. As they go further and further in, the other robots actually come and try to maintain the communication link, like a chain, to the extent we can, while it hasn't branched out too much. As they explore the environment, we build this high-resolution 3D map of this underground GPS-denied environment. And this process is being done in a decentralized multi-robot fashion because the course is so big and time is so limited. Each robot is mapping part of the environment, and when they meet each other, they share data, or they say, oh, I have seen that part, it looks like your map has that part of the environment, and they match it and create a seamless, larger environment. Perceptually, the course is quite degraded. We need to traverse through fog, smoke, dust, and so on. Similarly, traversability-wise, it's really harsh environment. This is some tests in Arch Mine that 900 feet under the ground, our team was doing in West Virginia, that the robot needs to understand the details of the terrain around it and avoid, and to understand what is traversable, what is not. And if a part of course is not traversable for certain robot with certain capability, as you saw in the previous clip, a more capable robot goes and explore and being dispatched to that area. There are a lot of multi-robot behaviors in this course because robots need to go, share the data and explore the environment together. Here you see obstacle avoidance. This is my favorite one. The third robot finds this very narrow passage between robot 1 and 2 and goes through there and start searching, the other side of the course. And then the other two robots understand that's the case, and they change their priorities and, dispatch the rest of the task among themselves and start searching the other parts of the environment so that we can, respect the mission duration time. These multi-robot behaviors can become quite complex. So we have this backbone of software in the loop, a very high fidelity simulation environment that we run intensively all these multi-robot behaviors to V&V them, verify and validate them before we basically deploy them to make sure, we have the right performance that we need in the course. robots, the scoring is about finding these interesting science targets and artifacts. So the robots search for those. Here you see what Kian, our operator, sees from the feed of the cameras when there's communication. And in the right-hand side, you see right-hand side, you see the machine learning, acting on these data feed and suggests to our human supervisor what is interesting size, what's the anomaly in the environment, what are the artifacts, so that we can report them to DARPA. At the beginning of the course, robots are dropping these communication nodes as, to maintain them, to create a mesh network, so that at least closer to the entrance, we talk to the robots, and so that if they find an artifact or a scoring object, we can see that in the human console. But as they go in, we lose that communication. They're autonomous. Here you see a robot that we're out of communication for about half an hour, and then when it comes back, it dumps this huge amount of data, and we just build a map, and Kian now has to deal with a huge amount of data, come in and report them to DARPA for scoring. Sometimes there's not enough time for robots to come back and send the data. So we have this capability, we call it data mules, that are faster robots that fly in and go in pre-mapped areas. Here you see a flying version of those. So we are, let's say 5 minutes to the end of mission, and those slow ground robots don't have time to come in. We send these aerial robots, and they take off and go in. They search environment on their way, but then they get to that slow robot that has a lot of valuable data, grab the data, and return it back to the surface, so that in the 60 minutes, we can retrieve the data and get the score. One big challenge with drones is their lifetime, right? So because of all these autonomy capability, they can only last 5 to 10 minutes. So for the last 2 years, our team has been working on this JPL patented idea. We call it Rollercopter. It's a drone that is designed to mainly roll on the ground to save energy and live longer. But it can fly when needed. When it reaches to an obstacle that is not rollable, it flies, lands on the other side, and continues the mission. Here you see takeoff and entrance of Rollercopter into one of DARPA-sponsored events. In the right-hand side, you see the hazard avoidance, and bottom left showed how drone is capable of flying in such a perceptually degraded environment with dust and fog and smoke. So I hope this kind of gives you a big picture of what at least how the 2019 course looked like, some of our robots and capabilities. But in terms of numbers, these are the capabilities we have achieved in the first year of this effort. As I mentioned, we went with COTS in terms of mobility. We didn't invest in building new robots, and we went with the existing systems and pushed on software and brain of these systems. And we were able to integrate Nebula, the Autonomy Framework, on 10 robots that you see here on this stage. Here, the Nebula, for example, on this spot. And on each robot, there's a different, basically, implementation of Nebula has been installed. And we were able to autonomously, operate 5 of these robots simultaneously in the mission. So we ran, 5 robot simultaneous missions. In ArchMine, our robots, a single robot was able to go more than 1 kilometer in a harsh environment fully autonomously and traverse more than 1 kilometer. And we were able to map more than 2 kilometers fully autonomously in a GPS-denied, COM-denied environment. So that was kind of in numbers where we were at before the competition. And that performance led to the second place in the first round of the DARPA challenge. Happy that. Which we were very excited about because it was the best for JPL, Caltech, and MIT in the history of DARPA challenges. So we were very excited about it. And but it's very important to mention this was a huge collaborative effort with JPL family. I mean, many of you, we have bothered you, you know about us, and it was such a fast-paced project that we needed a lot of support, and we were just getting super kind support from everyone, and especially from leadership on advice, encouragement, support, and from all the JPL family, from acquisition, shipping, receiving. Even before item is here, we were there, asking for the item, and 347 staff traveled for all our trips and testing, education office for all amazing interns and postdoc office, everyone. So thank you very much. This was a huge collaborative effort, and we learned so much about JPL and how kind the community is. Also, I want to thank the team members. So overall, maybe people maybe closer to the project have seen how hard these guys were working day and night, and they were super dedicated to JPL's reputation and making sure we are going to have a credible and successful performance. And our resources probably maybe was an order of magnitude less than some other teams, but these guys were just incredible, and I was super lucky that worked with these guys during the last 2 years. So at the end of the talk, I'm going to ask them to come on this stage so that you see some of the faces. So that kind of wraps up the first part of my talk, that how the competition went and what this, what kind of motivated the start of this. But really, the main intent and the main goal here is really not the competition, right? So what we are trying to do here is to add capabilities to JPL and try to pave the way or help other, other flights, current flights or future flights. So the main long-term goal is really, as JPLers, people love space here, is to fly Nebula or help other flight projects by leveraging components or parts of Nebula and enable those. And I'm glad to say we are taking some initial steps in this direction. So the performance in the competition kind of attracted attention from different entities, including NASA's Science Mission Directorate. And now we have been invited actually to be the technology arm for a cave exploration project in Martian analog caves in Northern California. And I'm very happy to say Jennifer, actually, who is the PI of the project from Ames, is visiting us today. And we are starting this collaboration with Ames, and we are being, the technology arm of the project. And we would love to put more instruments from JPL on these robots to explore the caves. We also are working with JPL scientists and scientists around the world, including Penelope Boston, #1 cave scientist, to push and write white papers to push for next decadal survey and push cave exploration into next decadal survey. What we are hearing from scientists is they are very confident it's going to be a big part of next decadal survey, so we are trying to help them with the technology part of that. And of course, the main goal of this talk is to raise awareness that what kind of capabilities we have been working for the last 2 years. And if you see any synergy with the projects you're working on, we would love to work with the JPL projects to integrate Nebula into existing projects at JPL. So for that purpose, for the last one, then I will go over the Nebula and tell you a little bit, very touch what it can do. So Nebula is a framework for autonomy under uncertainty. The unique thing about it is how it treats uncertainty, right, inherently. And uncertainty in measurement, perception, communication, in command execution, environment, and other parameters of the mission. The mission here, statement here is we want to autonomously assess and predict uncertainty, possible outcomes, and risk in uncertain environments to enable coordinated multi-robot missions in exploration of hard-to-access and unknown areas. And a little bit going deeper, it basically, the way it's kind of different from some traditional frameworks is it tries to treat uncertainty proactively rather than waiting for something to go wrong and react to it. And in that sense, the spirit of it is like PUMDPs, and it's basically trying to come up with approximations and make a PUMDP framework computationally tractable. So just in simple terms, the way you can think about it is, traditionally, you have these autonomy frameworks with a lot of modules, localization, mapping, planning, control, and so on. You can think of Nebula pictorially as a framework that formulates the problems on the edges, right? So because it deals with uncertainty, and uncertainty tends to couple the modules, right? It impacts, and it models these joint distributions and basically formulates the problems on these edges. Let me give you a concrete example. If you remember maybe one item from the technical part of the talk, this is a good example to remember. The localization problem, the problem of where the robot is in the environment, and the mapping problem, the problem of how environment looks like, are two fundamental problems in functional level robotic autonomy, right? And then there is this famous problem called SLAM, that stands for Simultaneous Localization and Mapping, that solve these two problems simultaneously. The interesting and important fact is solving SLAM is quite different from solving localization and mapping and putting them together. While a SLAM solution is robust and field deployable, localization and mapping, solving them purely and individually is more an academic effort, because when you deploy them, since their interaction is uncertainty dependent, the solution is brittle and not robust in the field. So you can think of Nebula as a framework that looks at the other edges and creates problems and formulates problems like a SLAP, simultaneous localization and planning, or SMAP, simultaneous mapping and planning, or other edges that I'm abstracting at this point. But with that framework, it tries to incorporate uncertainty a priori and proactively into the decision-making process, and hence remove one of the causes of brittleness of autonomy frameworks in today's systems. So let me go a little bit maybe into concrete examples. I'll give you 6 concrete examples of what Nebula can do, so that if you see part of it useful or synergistic with your efforts, we can dive into that offline later. But I also want to start by saying that to create this ecosystem around Nebula and work, expand it within JPL, we are building a website that describes all the capabilities. The code is available. It's a very quite modular piece of code, so we can integrate different pieces of it into the various projects. And software-wise, it has been implemented in ROS and F Prime now, and we're extending it to other software frameworks as well. Thanks to the Sub-T project, many components are field hardened and published. So as a first feature or example, I want to highlight the versatility of it. So we are dealing with complex missions where a single type of robot is not enough or capable enough to handle that mission. So we need to work with multiple robots with different capabilities, each one coming with maybe different processing units. One might have Qualcomm Snapdragon on it, the other one might have a version of high-performance computing, and so on. So with that in mind, we initially architect the Nebula in a way that it's modular and you can adapt it to the level of computation that is available. And that's what you see on these robots. Our drones are much less computationally capable than our Husky robots, and the same with the Spot and so on. But the framework is modular and capable enough that you can adapt it. Second capability is Nebula's navigation abilities. We have to deal with GPS-denied environments. We have to handle variable lighting from full dark to lit environments, so high dynamic range. We need to handle fog, dust, and perceptually degraded environments. We need to handle self-similar courses, because tunnels and caves might be very similar to each other as you move, and the water can create reflective surfaces and all that. Nebula has this complex navigation backbone software that can work with multiple heterogeneous sensors, ranging from LiDARs to radar to visible camera, thermal cameras, IMUs, and so on, each of which can work well in certain parts of the environment. And then again, back to the spirit of uncertainty awareness, it tries to model the uncertainty of these sensors, fuse them locally, and then again model the uncertainty, and offers a framework that seamlessly can switch from, let's say, a visible camera to thermal when you have dust, and from thermal to LiDAR when you don't have variation in the temperature and so on. The third capability is the topological mapping capability, which is one of the dimensions Nebula is pushing a state-of-the-art the most forward. So the goal here is to create a high-resolution 3D map of these GPS-denied environments. The maps would be up to 8 kilometers long, and we only can tolerate 5-meter error. And that's where this goes far beyond the state of the art. Like 5-meter error in 8 kilometers is even far beyond the literature in academia. And since the time is limited, we need to do it in a distributed multi-agent fashion. So in Nebula, we have this software backbone, we call it LAMP, large-scale mapping and positioning, that creates this factor graph that captures all the constraints coming from robot motion, robot to environment measurement, and inter-robot measurements. this factor graph then gets translated into a giant optimization that is multi-constraint and non-convex, and an elegant mathematical backbone converts that to a convex optimization. We solve it there, we return it back, and with that whole process, the level of capability we have been able to get is, so far, is reach 1% error over 2 kilometer-long GPS-denied courses. And we have been able to do so with 5 robots simultaneously. So we just, for this talk, we created some familiar maps for you so that you get some sense of what this lamp is doing. So top left here is the 301 map, indoor map, the building 301. You see in top right, Arroyo parking structure with all the beams. And in bottom left, you see an area around building 82 with all the trees and stairs and so on. And all these maps have been created in a matter of minutes only. So you just run the robot autonomously, it collects the data, and map is there. And in the right-hand side, you see an underground mine environment at Beckley, West Virginia, that we have mapped with LAMP. And as I mentioned, we have mapped up to 2 kilometer long autonomously using this framework. The fourth challenge Nebula is trying to address is communication. This is a huge challenge when it comes to caves and underground environments, because we are dealing with a non-line of sight environment. There's multipath environments that create unpredictable link qualities. We have to transfer large amount of data between multiple robots with low delay. So Nebula has this software backbone that can work with static and dynamic nodes. Statics are the ones that I mentioned that we drop like breadcrumbs, and Nebula basically suggests what is the optimal location to drop a communication node based on the geometry and signal quality. Also, when when you don't have enough communication nodes to drop, it helps the system to say, okay, the mobile node, this is the optimal location to go, or mule the data from that robot to this robot, because this link is the most useful link in the graph. And it also, in the background, handles all the dynamic routing and handshaking and intermittent communication between various nodes. The fifth capability is autonomous task allocation. So the environment is unknown. We have to handle intermittent communication between various agents. We need to handle degraded health. We might lose a robot. Environment is it's so harsh. We might have dust or something covering a sensor. We might lose a perception health. So handling all this risk and deciding which robot should go, what part of the environment at what time, is a big part of Nebula Framework, which it does it in a 3-layer software. At the top, we have the software in the loop, VNV process that runs multi-robot algorithms and says, okay, it has a performance that can be deployed. In the middle layer, we quantify risk and uncertainty in decisions that Nebula is making. And at the lowest layer, we handle the traversability, which is robot-specific. And the final, or sixth capability I have here as example capabilities is machine learning aspect of Nebula. Machine learning has 2 important roles for us within Nebula. Number one is it helps us to autonomously identify anomalies and science targets in the mission. And it also helps us to understand the environment semantically. What is a passage? What's a dead end? Where is the vertical shaft? And so on. Also, the second role of machine learning is to help us to adapt our models to the environment. So our ground robots, area robots, over time try to learn, okay, this is how loose the soil is, the sand is, and adapt their behavior and move more efficiently in the course. So I hope kind of these 6 examples give you a high level and very brief, of course we don't have time to go deep into this, but very high level idea of some of the things Nebula can do. The Nebula 1.0, version 1.0 is out now. If any of these modules or capabilities might be synergistic or useful, we would love to work with you, integrated in other JPL projects and expand the Nebula in JPL community. So with that, I would like to kind of leave you with a few thoughts. We all know, I think, the future of JPL and space exploration is much more autonomous, right? As we are targeting more complex missions, as we are targeting further destinations, higher levels of autonomy are inevitable. Similarly, industry is moving really fast in this space, in this domain, for terrestrial applications, of course, and for certain types of autonomy. So Nebula is pushing robotic autonomy boundaries, and in particular when it comes to safety critical systems and when it comes to unknown and uncertain environments. So we believe there's a huge opportunity here. With the DARPA challenge culture around this, with its fast pace, JPL has been able to build capabilities and increase the TRL level from almost 0 to 1 in some of these capabilities, all the way to 3, 4, 5, only in 1 year. And we believe, there's a faster growth coming, and there's a large and big opportunity here at the end of this project, and we are hoping basically be able to, extend it to further projects and leverage these efforts. Also, these efforts and the success of the team has been able to attract a lot of partners and talent to JPL. Here you see just some of the industry partners that we have be partnered with in the first year of the project, which we believe as we go further in the autonomy, they will be strategic partners for us down the road. And as just going back to the first message of the talk, of course, the main dream here is to create a first mission to a planetary subsurface void or caves someday. And we are taking very small initial steps in this direction. There's a long road ahead of us. But we believe with the software that we have now, with the solutions so far, we are at a good position. It's a great time to engage a larger JPL community, get advice from you guys, and steer the direction of project to a direction that minimizes the time to infusion into future flight missions. So we would love to talk to you guys and explore those paths moving forward. So with that, I would like to thank everyone for your attendance, and I want to ask the CoSTAR team members, please come on this stage, and I will play a short video that shows some of the fun we have had in the background. We'll probably also take a quick picture with all of you, the whole JPL community, and okay. So like this. Okay. Sorry. I think we just have 10 more seconds. Don't worry about it. Take it so fast. It's okay. Can you ask the audience to stand up? And are you visible? Audience, stand up.
There we go. Nice backdrop. All right.
Thank you. Okay, and with that we are ready for questions, and we have time for questions, and yeah.
I have a question.
Yes. So who is handling the microphones? Maybe go ahead.
Congratulations to the team. And Ali, question I had was, if you were to pick 3 challenges that you could solve.